So what we're going to start with is vector fields, and then we're going to move into line integrals. We already have a question. Is the final going to be only on a new material? Nope, it's going to be cumulative. It's going to be in the whole thing. In fact, a lot of the stuff in the final, we need all of the earlier stuff as well. But this is certainly going to be building largely on the content between 2 and 3, exam 2 and 3. So what we're going to do is consider a vector function. Where I have some function f of x and y that is a vector with component functions p and q. If some domain D is a subset of R2, then this vector function creates a vector field. Over the region D by assigning a vector to each point x and y in this region D. So basically imagine, yes, this is chapter 13. So basically imagine that, instead of inputting x and a y and getting a scalar back, we're inputting x and y scalar values, but we're getting a vector back. So any location x and y now has a vector that's associated with it. The field is continuous or differentiable if all component functions are continuous / differentiable. So if my component functions are continuous, my field is continuous. If my component functions are differentiable, my field is differentiable. So what does a vector field mean? Like, how do we interact with vector fields? We do. Electric fields are vector fields. Gravity is another great example of a vector field, right? The force of gravity that's pulling us down to Earth could be illustrated as a vector field, right? Because at any given location, you have a force that's acting on you. But it's not just the magnitude of the force, it also has a direction. So you might have seen previously that the magnitude of some force due to gravity was your mass times the mass of the other object times the gravitational constant g, and then you'll have the distance between those two things squared, right? So that might have been something you've seen before. You just might have written this a little bit differently, not the magnitude of some vector, but just as the force, right? Well, another way that we can write this is, say, with r being the magnitude of some vector x, where x kind of illustrates the vector that points between the two objects. So it turns out that I can write the force as negative m, capital M, g of the magnitude of x cubed times x. So x is here the vector that points between the two objects, and the force of gravity is necessarily negative because it's pulling you towards it. And you have these masses, and the only reason this is cubed here is so that we get the unit direction, basically. We still have this r squared on the bottom, and then we create a unit vector that's in the direction that the force is going to be pulling in. Okay, so that's just an example of vector fields that interact with us every day. So let's do an example where we start to kind of look, or maybe start to plot out a vector field. So we're going to sketch. The vector field that's given by x, y. So here on the left, why don't we actually make a little chart of some test points? So if I input x and y, I'll get some vector back given by my vector function. So what happens if I input the origin? Well, I get the 0 vector. If I put in 0, 1, of course I get 0, 1. And you can kind of see that this isn't too crazy of a vector field. So anytime I input some point, I get the same vector back. So let's just do a few more. And I think by now we've pretty much got the pattern. But let's plot this out. So first, I'm going to go ahead and plot some points here. We've plugged in the origin. Maybe we've plugged in, this is 0, 1. And then maybe we've plugged in 1, 0. And then 0, negative 1. And then negative 1, 0. And then maybe we've gone ahead and actually plugged in these corners here. So what does this vector field start to look like when I start to plot? Well, here I've got the 0 vector, so I don't really have a vector present here. But as soon as I hit 0, 1, I know that this goes 0 in the x direction and then 1 up. So it looks like that. This one is 1, 0. So we only go 1 in the x direction. And you can start to kind of figure out what this starts looking like. Something like this. Now these guys, this is 1, 1, so the vector here is 1, 1. So we start to kind of almost radiate from the origin here. And the further that we get away, right, the larger x or y that we have from 0, the larger the vector that is established at that point. Okay. Let's talk about gradient fields. The gradient field of a scalar function f of x and y is the vector field created by the gradient of f. So remember the gradient of f, this was partial f, partial x, partial f, partial y. So we have some scalar function, we take its gradient, and now we create a vector field out of that thing. That is a gradient field. A vector field that we'll call capital F is called a conservative vector field if it is the gradient of some scalar function. F such that so we're given a vector field, maybe by some reason we know it's conservative, then we know that it could be decomposed as the gradient of some scalar function f. So if we ever have this property where the vector field can be written in such this way, it is a conservative vector field. And those are going to actually have a lot of nice properties later on in this chapter. If this is the case, we say that f is called the potential function. And if you've taken maybe some physics classes, you'll have a potential function. This is where this is coming from in mathematics, is that you have a conservative vector field and you can decompose it in this way. Okay, so that's kind of pretty much it for vector fields. Now we're going to start talking about line integrals. Line integrals. Okay, So again, let's keep this idea that these sums or integrals are sums rather than just some area underneath a curve, or they serve some general purpose, right? It's primarily that they are some sum. So with that in mind, let's consider some curve C in R2. So maybe I start over here, and maybe I loop around like this, and then I end maybe somewhere over here. So if the curve has a value given by some function x and y at every point x and y along the line, one question is, what is the integral along this line? Right? If I wanted to add up all of the values that are restrained to this line, how would I add those things up? So, like always, we're going to start with an approximation and then get better and better and better until in the limit we arrive at the true answer. So I look at this curve, and maybe it's given by some weird relationship. But what we could always do is go back to parameterizing this curve. So let's go ahead and come up with a parameterization. So maybe we say x is now a function of t. We have that y is now a function of t. And we also say that t is bounded between some a and b. And this is to describe our path C now. So this constructs a position vector. That we'll call R. And this simply just points to the location on C that we're currently located at, given the parameter t. Now, if I wanted to approximate the values along this curve C, what I could do is break up this interval into smaller intervals, right? I could take the halfway point and then cut it up a little bit more and cut it up a little bit more, and then just kind of approximate this with straight lines in each segment rather than these curves. So we divide our parametric interval a to b into subintervals. Where these go from ti minus 1 to ti. So this translates to using really small arc lengths of the curve that we're going to try to approximate with these straight lines in each of these subintervals. So these are small arc lengths of the curve. And we'll call those delta SIs. So the approximation of all of these small arc length will be the sum of I equals 1, 10, sorry, to n, f of xi star, some evaluation point in each of these segments, yi star times this small arc length that we're taking. And then we just have some evaluation points. So kind of just do an illustration of what's happening here. Let's draw a little bit smoother of a curve this time. So maybe we're doing something like this. What we could have done is taken some halfway point, and now we have two intervals. And now I'll break that interval up with straight lines like this. And then maybe I say the halfway point is my evaluation point. So then I add this, and I add this, and I get an approximation. It's not very good, but it's still a reasonable place to start. And then what we could do is slowly start to do more of these things. So now we have here, and here, and here, here. So stuff like this. And you can start to see that if we start approximating these with straight lines now on each of these little subintervals, it's not so bad. And this was the whole premise of doing just an arc length integral. But now we also have values along this path, not just taking the arc length of the curve itself, not how long this curve is, but adding up all the values along the curve. So along each of these intervals, I have some evaluation point that we're adding. So I have something maybe here, I have something here, and then I start to add up all of those values along that curve. And of course, if we make those smaller and smaller and smaller, we get better of an approximation until in the limit, if our path C is smooth enough and the limit exists, we end up saying that the line integral over C, f of x, y, ds is equal to the limit as the change in s goes to 0 of the sum I equals 1 to n of our approximation. So f at xi and yi star at our delta si. So this is how we write a line integral. So this is with respect to the arc length, this ds. So how do we go ahead and evaluate something like this? Well, in Calc 2, we discussed arc length, and we've done some arc length in this class as well, where we said that the element of ds was dx dt squared plus dy dt squared times dt. And in this class, we related that to the magnitude of r prime dt. So thus, given our parameterization, our line integral over the path c of f of x and y ds is the integral from a to b f of x of t, y of t, and then our square root of dx dt squared plus dy dt squared dt. So even though we did this in R2, this relationship extends to Rn. So rather, we can write still same notation on this side. We still might have some line integral over c of some function, or input x, y, z, and so on. ds, this is the integral from a to b of f with our parameterization times the magnitude of r prime dt. Because no matter what dimension we're in 2 and on, a line still follows a path, right? And we're still taking a one-dimensional thing along that. We're still trying to add up all the points along this line. So it ends up just being this single integral, regardless of how many higher dimensions that we involve. So let's do our first example. What we're going to do is evaluate the line integral over c of x, y to the fourth ds, where c is the right half of the circle x squared plus y squared is equal to 16. Traced counterclockwise. Okay, so let's first draw out what C looks like. What does our path look like here? Let's go ahead and draw a circle centered at the origin. And we said that we're only interested in the right half. So let's go ahead and see if we can erase this left half here. And we also have an orientation, right? This is counterclockwise. So we know that we're traveling in this direction like this, right? And we start down here and then we end up here. This has a radius of 4. So imagine our position vector is this vector that comes out from the origin and comes out to the curve, and it has always a magnitude. Oh, sorry, yeah, no, it has a radius of 4. That's right, radius of 4 here. Okay, so very first thing to do is to parameterize this circle, our path. Now, moving forward, we've talked about parameterization curves before and how there's an infinite number of ways to do this. It's still true here. We can do an infinite number of parameterizations as long as it accurately draws out the region that's being described. So this is the parameterization that I've chosen. Maybe you can choose something else. Maybe it's worth getting some practice with trying to do these parameterizations. I feel like a lot of students struggle with this aspect of line integrals, is the parameterization portion. So what I'm going to do is I first set an x and a y. So I say I have an x and a y function. And circles are pretty easy. I basically think whenever I see a circle, I think sines and cosines. So if I want to say x is going to be 4 sine of t, that's perfectly fine for me to put a sign here on the x as long as I am consistent with what I'm choosing for my, my interval for the parameter t. So let's say I say that t is bounded between 0 and pi. In this interval, we start with sine of 0, which gives us 0, right? I don't have any x component here, but I do start to slowly increase. I come out and I finally reach 1 when t is pi over 2. And then I come back and I'm still remaining positive all the way until I get to pi again. So 4 sine of t accurately describes the x values for this circle from 0 to pi. For y of t, what I could choose is I need to make sure that I start negative. Okay, so I could choose negative 4 cosine of t. Right, so I could choose, if I plug in 0 here, I start at negative 4. I finally reach y is equal to 0 at pi over 2, and then I continue onward. And then when I get to t is equal to pi, I end up with a 4 here. Now, this isn't the only parameterization. You could have chosen, 4 cosine t for x, and then 4 sine of t for y, and then chosen some interval, maybe like negative pi to pi. That would also work. That's perfectly fine. But they always have to be self-consistent within your interval here. So now that I've formed my parameterization and I've kind of done some checking to make sure that my parameterization is accurate, the next thing I'm going to form is the ds, right? So I need to find dx dt. For this is 4 cosine of t. And then my dy dt is 4 sine of t. So ds is equal to this squared. So I get a 16 cosine squared t plus a 16 sine squared of t times dt. In other words, these cosine squares and sine squares can group up and equal 1, but if I pull out their like coefficient, all that I'm left with here is a 4 dt. So that's how ds relates to our parameter t. So then what I do is I go back to my original line integral, and I say the line integral over the path c of x y to the 4th ds is equal to 0 to pi. That's the interval of my parameter. Then I have 4 sine of t, -4 cosine of t to the 4th times 4 dt. Just rewriting just a little bit. This is 4 to the 6th sine of t cosine to the 4th of t dt. So we could try to do some trig substitution here, but I really like that this is to the 4th power and that this is to the 1st power, because I can do a little sly note here. That if I thought about taking a derivative of cosine to the 5th of t, I would get -5 sine of t cosine to the 4th of t. And here I have that sine of t cosine to the 4th, right? So if I brought over this -5 over to the left-hand side, I could rewrite this guy as a derivative. So an integral of a derivative is really nice. So here, this is -4 to the 6th over 5 cosine to the 5th of t, evaluated at t equals 0 and t equals pi. This is 4 to the 6th over 5 plus 4 to the 6th over 5, or 2 of them. This ends up being 8,902 over 5. So that was our first line integral. Let's do another example. So let's consider the path straight from the origin. And then after we write out this problem, we can take our 5-minute break. So we're going straight from the origin to the point 1, 1, 1. Oh, no, we're going from the origin to 1, 1, 0. Then straight to the point 1, 1, 1. Our goal is to evaluate the line integral on C of x minus 3y squared plus z ds. Okay, so let's go ahead and take our 5-minute break, go grab some water, go use the restroom, and we can come back in about 5 minutes. Okay, let's pick back up. So we're going out from the origin to the point 1, 1, 0, and then we go straight from 1, 1, 0 out to 1, 1, 1. So what's kind of happening here? Let's do a quick plot. So we have our x, y, and z. And then we're going out from the origin out to this point. Let's do actually line like this. We're going out to some point, 1, 1, 0. And then from there, we go straight up until we hit our terminal point. So we go from 0, 0, 0 to 1, 1, 0, and then finally to 1, 1, 1. So we can't have a really nice one-all parameterization for this entire curve C. So what we're going to have to do is break this up into a C1 and a C2. And we'll have to do parameterizations along each of these line segments. So for C1, our parameterization we'll call R1. This is one of the parameterizations we could choose. If we say x is equal to t, y is equal to t, and then z is equal to 0, and we go from 0 to 1. Then we need to parameterize our second curve, C2. Now, it doesn't need to, this new interval on C2 doesn't need to start at 1 and end somewhere else, right? These are independent of each other. This t is not, you don't have to think about it as time, it's just some parameter, right? So what we could do is say that this is always at 1, 1, but then goes from 0 to 1 linearly. We can also choose the interval 0 to 1 here. That's perfectly fine. So now when we calculate the line integral and we break it up into these regions, we have to find what r prime is on both of these segments. So remember, this is trying to find ds. So in the interval for C1, we say that r prime is 1, 1, 0, and the magnitude of this vector is equal to root 2. On C2, we should put our subscripts here. So R2 prime is 0, 0, 1. And the magnitude of this vector is just 1. So our line integral over C of our integrand, I'll just write it as x, y, and z for right now, ds is, first off, we're breaking this into 2 segments. So we're doing 2 line integrals like that. This is the integral over C1. And our integrand was x minus 3y squared plus z ds. And we also have our second line integral, C2, of x minus 3y squared plus z ds. So now, for each of these line integrals, we did a parameterization. On the C1 segment, we went from 0 to 1. We said that x was t, and we also said that y was t, and z ended up being 0. Our ds was square root of 2 dt, so that's why I have the root 2 dt here. For the second segment, we still went from 0 to 1, but this time x and y were 1, and now z was t. So here we've got 1 minus 3 plus t, 1 times dt. So we'll just have a dt here. So we actually can go ahead and take these integrals. So we can move this root 2 outside, and then we can have a t squared over 2 minus a t cubed evaluated at 0 and 1. And then over here, we can have a negative 2t plus t squared over 2 evaluated at 0 and 1. So this gives us a root 2, 1/2 minus 1 plus a negative 2 plus a 1/2. This ends up giving us a negative square root of 2 over 2 minus 3/2. So now we can break up these segments, right? So we didn't have a way to kind of characterize the parameterization for both of these in one go. So we had to break up our path C into 2 different line segments and then find the line integral over each of those by doing parameterizations. So the next thing we'll talk about is mass and center of mass. So a physical meeting of the line integral of f ds could be to calculate the mass of a very thin wire that has some variable density. So what we could do is say the mass is the line integral over the path C, which describes the wire, and then have some some linear density. That's typically written as rho in physics, so we'll use that here. So rho is a density in mass per unit length. So if you have like some thin wire, maybe you've bent a paper clip and maybe you melted it down so the density was a little bit off. This is a way to calculate the total mass, right? Some variable density along the line here. The center of mass is still a point in XY. And notice that it doesn't actually need to be on the line, right? Maybe something doesn't have its center of mass exactly where it exists. So that means that you can't really balance it, right? So our x bar is 1 over m, the line integral of x times the density ds and y bar is 1 over the mass the line integral of y times the density x times y ds. So this is just one application of doing these line integrals. We have these density functions, right? Basically, more or less, they're just our integrand f of x and y, right? Now we're just assigning a physical meaning to them. So now let's look at line integrals with respect to x and y. So sometimes line integrals are taken with respect to x or y rather than arc length. So imagine that I have some path that I need to take, but this time instead of doing a ds, I have a dx here. How do I translate that back? Well, we can still do a parameterization. It'll go from a to b of f of x of t, y of t. And then remember, so recall here on the side that I can write x prime as dx dt. So that allows me to find out what this dx is. This is just an x prime of t dt. Likewise, for a line integral with respect to dy, I can also do a parameterization. But this time I'll have y prime of t dt. Sometimes these two types of integrals appear together. So there's a shorthand that kind of goes in with them. Maybe I have some line integral of some function a of x and y dx, and then I have another line integral over that same path c, but this time it's over some function b of x and y with respect to y. A shorthand way of writing this is the line integral of a dx plus b dy. So basically it just drops the second integral here and says this is all line integral over the path c, but this part of it is being integrated with respect to x, and this side of it is being with respect to y. Okay. Orientation. So notice that this kind of one of the problems specified an orientation that kind of goes with the path. So how much does that really play a role here? So if we reverse the direction of C, what happens, right? If we have the initial point be the terminal point or vice versa, what's going on here? So we say negative C is C with the opposite direction. And let's look at what happens with our line integrals. If I have the line integral of negative C of f of x and y dx, I end up with negative the line integral over c of f of x, y dx. If I do the line integral of negative c over f of x and y dy, I get negative line integral over c of x and y dy. And finally, if I go with the line integral over negative c of f of x and y ds, then I end up with the positive line integral over c of f of x and y ds. So the reason that this one stays positive is, notice that if you're traveling in the opposite direction, x and y change sign, but ds is always a arc length. Arc length is always a positive quantity, right? Regardless of which direction that you're going in. And you can kind of think of it as that absolute value, right? It's the magnitude of r prime dt. That's never going to change sign. Okay, so that was kind of our introduction to line integrals. So now we need to start talking about line integrals where we have vector fields. So before, you can kind of write what we've already discussed as scalar line integrals. These are now vector line integrals. So let's consider a path. In R2, that has a vector defined by our vector field, capital F, of x and y at every point. That goes along this line. So let's kind of draw maybe something where we've got a path, maybe something like this, but that at any one given point on this line, there is a vector given by some vector field that's associated with it. So it doesn't necessarily need to be along the line. It could be, pointed anywhere. So what does a line integral over this curve in a vector field kind of represent? What does this mean, and how do we kind of perform it? So what might be a physical example that we're trying to do? Well, think about work. Way back in the beginning of the course, we talked about work defined as a dot product between the vector of f and the vector that denoted the distance that's traveled. Now, that only worked for a vector d, the distance, that was pointed in a straight line, right? So here we don't have that. So maybe we wanted to calculate the work done by something in a vector field that denotes, the force that's being applied to the object at any given point. But now I don't have a straight path, right? Maybe I'm traveling around here. So how do I kind of calculate that? Well, again, we're going to try to break this up into small line segments and then approximate each of those segments with straight lines. So let's start by dividing the parametric interval again. This creates small arc length segment that we'll again call delta SI. We know work is defined as the dot product between F and D in a straight line. So if we wanted to calculate the work done along this path, well, again, we're going to try to recreate these small little segments of straight lines. So in order to kind of do that calculation, what we're going to do is recall the unit tangential vector, t, is the unit vector of the first derivative of the position vector, right? That's how we defined it. We said that t was r prime over the magnitude of r prime. It just points in the direction that we're heading. So let's put that in text just to kind of remind ourselves which points in the direction the object is moving. The distance traveled is approximately the small arc length component of t times t with x of ti star. This is our evaluation point. Y of ti star. So this is going to be our distance vector, right? It's the direction that we're traveling in times the arc length of that small little segment, the length of that segment, right? So this kind of gives us a distance vector. Now remember, we're on our little subinterval. So ti star, this evaluation time is just somewhere in that small little segment. So the work done on that small segment is f at this evaluation point dotted with the distance vector that we just said was approximately the length of that segment times the direction that we're traveling in. So what we could do is just add these all together and get an approximation for the total work done. So in the limit, as I let those arc lengths get smaller and smaller and smaller, we approach this line integral. So we add these up. Adding these up approximates the total work done. In the limit, we can actually say that the work done is the line integral over C of the vector field f of x and y dotted with t ds. So this is the first vector line integral that we're going to be looking at, right? It's just I am integrating over the path C with my vector field, but I have to, my integrand needs to be a scalar, right? So basically I'm traveling along the line given a parameterization, and the amount of f in the t direction is the thing that I'm adding up. So there's other ways to write this. Of course, we can't integrate with just ds here. We're typically going to do a parameterization. So what we're going to note is that t of x and t, y and t is some vector that's inherently just a function of t, which is r prime of t over the magnitude of r prime of t. Thus, we can write the work in terms of our parameterization of this curve. The integral from a to b of f with the parameterization plugged in. So this is x of t and y of t. It's more general for higher dimensions, like arbitrary dimensions, to just put r of t in here. Dotted with r prime of t over r prime of t. And then we substitute ds in for dt. So we have the magnitude of r prime of t dt. Now notice here this denominator is going to be able to cancel with the one out here. So we can write this as the integral from a to b of our vector field function with our parameterization substitute dotted with r prime of t dt. So this is just another way to write that. There are some shorthand notations for this as well. So sometimes people write ds as a vector, or they say d capital, not capital S. They say, where they have this t ds. Sometimes they write this like that. So this is another way that you'll typically see this thing, just as a shorthand. It just means that the arc length has a specific direction to it that's given by t. Okay, this is called a flow integral. The reason it being called flow is that what we're doing is we're adding up all of the components of the vector field F that are along the path, right? So the components of F that are pointing in the direction of the path, right? So imagine we go back up to our little plot all the way back up here, and I'm going in a very specific direction. So let's say that I'm going this way with my line integral. If I have a unit tangent vector that's pointed in this direction, I have to find the component of this that's in that direction. I have to find the component of this that's in this direction. I have to find the component of this that's in this direction, right? That's why it's called flow. It's because it's taking all of the components of these vectors that are in the direction of travel. So let's do an example. Given that we have a vector function, x, z, and y, let's find the line integral over C f dot, I'm gonna write it like this for a second, and then we're gonna back up. Another way that you'll actually see this is dr. So we have dr here is equal to, oh, no, that's just still the problem statement. When C is the helix that's given by r of t is cosine of t, sine of t, and t, when t is between 0 and pi over 2. So the first thing we need to do is find out what our vector field F is given our parameterization. So F of r of t is equal to x of t, z of t, y of t, right? And given our parameterization, this is cosine of t, t, sine of t. We also need to find out what r prime is. So r prime of t is negative sine of t cosine of t and 1. So the dot product between these two, f with r and t inserted, dotted with the first derivative of r, this is equal to negative cosine of t times sine of t plus t cosine of t plus sine of t. So my line integral over this helix of f dot dr is the integral from 0 to pi over 2 negative cosine of t sine of t plus t cosine of t plus sine of t dt. Okay, in order to do this integral, I'm going to make some notes. That if I wanted to take a time derivative of cosine squared of t, I ended up with negative 2 sine of t cosine of t. So that's like this first term here, except I just have this extra 2 that I can divide over. And I can also note that d dt of t sine of t is t cosine of t plus sine of t, which is this term here. So my integral then is cosine squared of t over 2 plus t sine of t. This is evaluated at t equals 0 and t equals pi over 2. We can do this evaluation out and we get pi minus 1 over 2. So doing these types of line integrals, it's not too much harder than the old typical line integral that we talked about earlier today. But all that's happening here now is I need to insert my parameterization into my vector function rather than a scalar function, and I need to dot it with r prime rather than multiply it by the magnitude of r prime. So note here that orientation of C matters. So this time, if I have a line integral over negative c of f dot dr, this is negative integral over c of f dot dr. The reason this changed is because now, since we're still doing this ds, but this time, remember, we've got t times ds. This might remain positive, but now this is pointed in the opposite direction. So that's why this negative now comes up. We may also write that the line integral of f dot dr is equal to the line integral over c p dx plus q dy plus r dz. Where f is equal to p, q, and r as their component functions. Right, and this goes back to taking integrals with respect to x and y, and then we've also thrown in a z component here, if this is an R3. And this makes sense, right, because this is a dot product, right? You can kind of think of dr as having this dx, dy, dz component, and then we have f being dotted with it, so this is the end. This is another way of writing this line integral. Conventionally, this is not the way that you would really want to integrate this. You might be given an integral in this form, but most of the time, I think it's easier to integrate it with regards to a parameterization. So moving forward, when you see a line integral, your first thought should be parameterization. Okay, so just kind of maybe a note for the future as well. We're going to see this come up, but this is still related to line integrals. If we have, say, a line integral or a path here, and we want to know, instead of the component of some vector that is along the path, so we would find the component of that vector along the path. This is the flow integral. We're going to encounter a flux. So this word is going to show up a bunch later. Flux means how much is pointed in the normal direction. So basically, I have this vector. How much is in this direction? That's perpendicular with the direction that the line travels in. A lot of ways that might be written as f dot n, right? This is the amount of f that's traveling normal to some path rather than f dot t. So we will encounter this. So this is in the scope of line integrals. This is a flux. How much is traveling through here? Now, flux is going to show up in line integrals. In what we're going to do later on is surface area integration, and then even in volumes, you'll have this flux term show up. Flux is the thing that characterizes how much is moving through a line, a surface, a volume. That's what flux means. So if you have a flux line integral, it's how much of the vector field is traveling through the edge, this line here, rather than along it. So we'll see that. We're going to start like building up this cool series of theorems that we're going to be able to refer to line integrals that translate to area integrals and vice versa. And then we'll have volume integrals that translate to area integrals and vice versa. So we're going to create these theorems that kind of connect all of the integrals that we've kind of been building up to. Okay, then with that, why don't we call it a day? We've got about 5 minutes left, so I'll stick around, answer any questions that you have. Otherwise, I will see you all tomorrow. Stay safe.